Hello, so today we're going to be talking about displacement time and velocity time graphs. So first of all, what is displacement? So displacement is distance but with a direction. So a point A can be said that it is 20 meters from point B. Okay, so if that's 20 meters away and I walk from point A to point B, then I've walked a distance of 20 meters and I'm also displaced 20 meters. If I then walk back, I'm displaced 0 meters because there's no displacement from A, so S is equal to 0. However, distance is equal to 40 meters because I've traveled 20 meters twice. Velocity is like a speed but with direction. So throughout that walk, I could have gone 3 meters per second the whole time, but on the first journey I'd be 3 meters per second to the right, and then on the second journey I would be 3 meters per second to the right or to the left, or minus 3 meters per second to the right on the second journey. Okay, so what I'm trying to say is velocity and displacement are vectors. However, they're numerically the same as speed and they're numerically the same as distance. So displacement has a unit of meters and velocity has a unit of meters per second. Time, on the other hand, is a unit of seconds. Okay, so in a displacement time graph, it would look something like this. And on the y-axis, you will always have displacement, and on the x-axis, you will always have time. Okay, so displacement is measured in meters and time is measured in seconds. Okay, you would then have some units, and we'll just go to 10, and we'll just go up to 5 on there. Okay, so we could basically say, if we looked at a graph and the question said something like, in the first 4 seconds, Jim is displaced 5 meters from his starting point. So if he starts at 0 meters, because that's his origin point, and in the first 4 seconds, he's displaced 5 meters. Okay, so he'd end up at a point of 4, 5, with t on the x-axis and displacement on the y-axis. Then that's going to be 4, 5 if we look at it with coordinates. If then Jim decides to stay 5 meters away from his point for a further 2 seconds, then he would be displaced no further. And if he came back to where he started in the next 2 seconds, then he would be back to 0 displacement, because essentially what's happening is Jim is starting at point A, which is 5 meters from point B. He's walking to point B, he's staying there for 2 seconds, and then he walks back to point A. Okay, so what we look at for displacement time graphs, which makes them quite interesting, is the gradient. Okay, so to work out gradient, it is rise over run, or y-axis over x-axis. Okay, so in our case, this y-axis is displacement, right here, and then the x-axis is time. So it is y-axis displacement over x-axis, which is time. So s over t, and if we were to remember our equations of motion, then s over t is equal to velocity. And I find a good way to remember this is s is measured in meters, time is measured in seconds, and s over t would be meters over seconds, which is the unit of velocity. I mean, that's not a necessary way to remember it, but I just find that that's quite helpful. So if we look at the gradient, then that's going to be in meters per second. So that's going to be our velocity. So we can say that the gradient for this starting point, so the x-axis he got to 4, and then the y-axis he got to 5. So rise over run would give us 5 over 4, or 1.25. In the next part of the graph, you can see that the gradient is going to be 0 because he doesn't move, so the velocities, there's no velocity there, and also a line that is straight across horizontally has a gradient of 0. And then in the last part of the graph, over 2 seconds, the person, Jim I think we called him, is travelling 5 meters back to his destination. So then his velocity in the same way would be a minus, first of all, and it would be minus 5 over 2. Or, minus 2.5 meters per second. This brings us on to velocity time graphs. So they'll look pretty much exactly the same as the displacement time graph, except velocity will always be on the x-axis, and that's measured in meters per second. And sorry, I'll put that in brackets. And then time is always in the y-axis, which is measured in seconds. So if we go again with the 2, 4, 6, 8, 10. In fact, if we draw exactly the same graph, just for quickness, and see what that means for the journey. So for the first 2 seconds, or well, in this case it's actually 3 seconds, and then 2 seconds. Okay, so 7 seconds, 5 seconds. Okay. Anyway, we'll call this 4 seconds, or 4 meters per second, sorry. So in the first part of the journey, we started off at a point A at 0 meters per second at 0 seconds. Okay, so he starts off at rest, or the ball starts off at rest, or whatever the object that's being used to get this graph, it started off at rest. Then within 3 seconds, it accelerated to 4 meters per second. And this is an acceleration because we can see that the velocity, or which is numerically the same as the speed, gets faster. And we know from, if we're ever driving in a car, whenever we go from a slow speed or from rest, and we end up moving, then to get to there we must have accelerated. For the next 2 seconds, the object remains at 4 meters per second, so the acceleration can be said to be 0. And then for a further 2 seconds, the object decelerates back to rest. Okay, so remember in the last example when we said that the y-axis over the x-axis gave us the gradient, which was velocity. In this case, if we use the exact same equation and the exact same reasoning, y-axis over x-axis is going to be velocity over time, which is going to be meters per second over seconds, which is meters per second squared, and that's acceleration. Okay, so our gradient of the line gets acceleration. So if we find out what the gradient of the line is, so for the first part we have the rise is 4 and the run is 3, so rise over run is 4/3, or 1.33333 meters per second squared. For the next part of the graph, this part here, there's no rise and the run is 2, but that doesn't matter because as there's no rise, 0 over 2 is equal to 0 over 2 is equal to 0 meters per second squared. So for the last part of the graph, if we find out the acceleration, then we're going to have a run of 2 and a rise of 4, and then it's going to be 4 over 2, which is equal to 2 meters per second squared. It's actually going to be minus 2 meters per second squared because we're going from 4 to 0, so we're decelerating, and we call that a minus acceleration, or it can also be called a retardation, which uses a bit of Latin. Furthermore, if we then find the area under the graph of a velocity time graph, then that is going to be finding velocity times time with some sort of prefix, but essentially velocity times time, which is meters per second times second, which gets us meters. So if we find the area under a graph, then it's going to be equal to the displacement. So for this graph here, we would find the area of this triangle, which would be a half times the length, which is 3, times the height, which is 4. So that's going to be 6. And then for this part of the graph, we would have just 2 times 4, so that would be 8. And then for this part of the graph, we would have half the height, which is 4, so 2 times 2, so that would be 4. So we've got a 4, 6, and 8. So the total displacement would be 18 meters. Okay, I hope that wraps up displacement well for you. Thank you very much for listening.